Yeah, it's a pleasure to be here today on this beautiful day. So my name is Lynsay Spafford. I'm a postdoc researcher at the University of New Brunswick. And I work with a team of researchers at, Anthony Taylor, also at the University of New Brunswick, and two researchers from St. Yves University, as well as the University of Laval in Quebec, and also James Steenberg from the Department of Natural Resources. And our backgrounds cover forest ecology, kind of operational forestry practices, and as well as soil biogeochemistry and climate modeling. So we have a kind of a broad range of expertise within our team. And I'll just also mention that we're funded by Research Nova Scotia through the Forestry Innovation Transition Trust Program for a 5-year project. So we're just starting our second year now. And so a big focus of what we do is on temporal ecology, so patterns over time, and that includes phenology. So phenology is the timing of events like, for example, when your leaves emerge in the spring, or when your trees change color in the fall, or maybe when your trees start to accumulate woody growth in the spring, or else when they stop growing. Those are all examples of phenology, the timing of seasonal events in nature. And we're seeing a shift in our phenology patterns in the forest over time. We're seeing an earlier timing for our leaf emergence in the spring. Typically in our boreal and temperate forests, it's about 2 days per decade on average. So over longer time periods, we're seeing quite a dramatic shift. For example, if we look at this image, I think I showed this last year, way back in 1868 at the end of May, we don't see the leaves yet out on the trees. But now fast forward to 2005 and we see the leaves out and quite well developed. So that's just one example of how we're seeing an earlier timing of leaf emergence and an earlier start to our growing season. And then, so you might think that, oh, maybe this is more opportunity for growth, that we're seeing a longer growing season with an earlier start and often a later finish. But at the same time, it could also lead to some complications. If we have an earlier start, then that often coincides with increased moisture demands for growth throughout the growing season. If we're hitting peak growth patterns when our conditions are kind of dry later in the summer. And it could also expose trees to more frost conditions earlier in the spring if they leaf out, and then we have a late spring frost within 2 weeks of leaf emergence. That's when our leaf tissues are very susceptible to frost damage, for example. And if we're also seeing a later timing for our fall colors, and the leaves are still metabolically active when we have a hurricane, then that could lead to some increased damage to those trees. So there's a lot of uncertainty. What are the implications about this change in phenology over time? And that's what we aim to address. So we've established a long-term network across Nova Scotia, and it's our goal to keep it going. And we want to set this up as a resource for people like yourselves that are interested in understanding the viability of different species in different locations across the province. And eventually we want to pool our observations and calibrate some predictive models so we can understand future patterns in phenology and radial growth for trees across the province. So this is the current look for our network. We have stations all the way from Yarmouth County to near Shetty Camp area. I established 12 stations at the start of my PhD back in 2019 on public lands. And then I added another 12 with my colleagues starting in 2024. And then just a bit about each of our stations. So we have 3 main types of infrastructure at our stations. So the first would be our Phenocams, which is short for phenology camera. It's a stationary time-lapse camera. Basically uses remote sensing kind of techniques, but it's looking at an individual stand of trees over time, and we can actually track at the individual tree level. So with these observations, we can create curves of relative greenness over time, and that helps us to know when the leaves emerged, when they changed color. And it can also help us to understand when there's kind of a health concern in the forest, because we see this reflected in the signal of the leafing vigor of the trees through the cameras. And here's a little example time lapse from one of our sites, just to give you a sense of what it looks like. We have a few different types of cameras. So this is an example using a trail camera, actually. And we have a reflectance panel that we use for our analysis. And then in addition to phenocams, we also have dendrometers at our sites. Pardon me. So this is a device which is very, very simple. It's just a little spring attached to the stem of your tree. And as the tree grows and shrinks, this presses and contracts the spring, and so we can measure the tree growth fluctuations every 15 minutes. So every day the trees typically shrink, around noontime, and then they expand at night when they refill with water, so we can track that diurnal pattern. And so anytime that the tree has a net increase in growth, so that means it's forming new cells and expanding beyond its previous maximum radius, then we consider that to be growth. And any fluctuations below the previous maximum, the tree is in a condition of a water deficit. And we're currently monitoring 12 species. So we have 6 hardwoods and 6 conifers. And one of our conifers is the deciduous larch there. Okay, now more into the drought impacts from last year. So just to kind of characterize the drought in a meteorological sense, here's some data from one of our stations where we have soil moisture sensors, and they measure what's called gravimetric or potential soil moisture. So this is how hard tree roots have to pull to get water out of the soil. And our sensor can measure up to 200 kilopascals of tension. And then anything beyond that is actually beyond the range of our sensor. So it was so dry at our sites that our probes dried out to the point where they couldn't even measure anymore. And so usually these kind of probes are used with farmers that have fields and they want to know exactly when they want to apply irrigation. And so you typically apply that at something like 30 kilopascals for most crops. So for us to exceed 200 kilopascals is quite extensive. And the probes actually couldn't start measuring again until we had a rain later on in the year. So that just gives you a bit of an idea about how severe the drought was at some of our sites. And we did see this even visually from our phenocams, that we have some early senescence in some of our trees. And then, so how does this compare to some longer term patterns? So a very important control of tree growth is actually how much moisture is in the air. That's called vapor pressure deficit. And when we see higher vapor pressure deficit, that means that it's a drier conditions. And so if we look at the vapor pressure deficit for just last year, using some long-term data sets, we can see that we exceeded the previous maximum ever observed in 30 years across the province for all of our locations. So it was very, very dry. And we saw this peak kind of later in the summer, around August 10th, in vapor pressure deficit. And now there's been studies across Canada where they've looked at interannual growth patterns, and they see that when you have an increase on average by something like 0.1 kilopascals in vapor pressure deficit, then that actually typically corresponds to something like 10% less growth. So for us to, we typically see our maximum summertime vapor pressure deficit around 0.5, but we were close to 0.8 last year, then that could translate to a 30% reduction in radial growth, for example. So it was quite severe. And so here's the data from our dendrometers showing daily growth patterns over time just for last year. And if we look at the date where vapor pressure deficit peaked, which was August 10th, that also kind of corresponds with the kind of peak in terms of interruption in growth patterns across our trees. So this drought was sufficient to interrupt their radial growth. So the trees had trouble refilling their cells at nighttime and continuing to grow due to the drought last year. And some species had less severe impacts from the drought, like for example, oak, which is a ring porous species, and it starts growing much earlier than other species. It even starts before conifers. And if we look at the curve for oak, the peak timing of its growth was well before the peak timing of the drought. Whereas a lot of our hardwood species actually otherwise had their timing of peak growth right around the timing of the peak drought. So these species might be more sensitive in terms of the temporal patterns of their growth. And our softwood species were also influenced. So in general, the softwood species did start growing a little bit before the other hardwood species. And I want to add that this is our first full year of dendrometer data, so we need more and more data in order to really compare the magnitude in the pattern. But this is really interesting to see because these kind of curves are really unusual. Usually we expect a nice, neat, bell-shaped curve that species continuously grow and then they taper off. They don't have this kind of interruption. But it was also neat to see that some species resumed their growth after this really, peak drought conditions. Like white pine, for example, was growing in October, which is kind of unusual, but they resumed growth after a long hiatus. And here's just a little kind of a more zoomed in look at one of our time series for a larch. And so when a tree has an accumulating nighttime water deficit where they don't refill their cells at night, and then the next night they have an even greater level of shrinkage, and so on and so forth, that's unusual, and that's what we observed here. We had a 12-day streak, for example, with this tree where it didn't grow, and we actually see accumulating water deficit at night for this tree. And then looking at some of the more broad patterns, just the number of days where trees were able to achieve growth, where they had enough moisture and the conditions are right. We actually see that balsam fir and red oak had the greatest number of net growth days, which I was surprised to see. I've heard a lot about balsam fir, and my colleagues have found that a lot in their own studies, that balsam fir is particularly susceptible to drought and heat, and yet in our case, they happen to have the second most net growth days. Although something that we're really interested in seeing is the growth patterns this year, because we often see kind of a legacy effect, and the balsam fir could have been using reserves from the previous years as well. So we'll wait to see how balsam fir performs this year as well to really understand the full picture. But it's neat to see, for example, with red oak, that they started growing the earliest, and they also had the greatest opportunity for growth in a sense, with the greatest number of net growth days. And unfortunately, on the other end, we see black spruce and larch had the fewest days with net growth where they were able to achieve growth. So the drought was really, really hard on them. And then, yeah, as I mentioned, if we look at the timing of the growth start, we see that red oak and balsam fir started growing the earliest. And sugar maple was actually one of the later starting for our hardwood species, as well as white birch. Okay, so in summary, the kind of the impacts, the immediate impacts we can see is that the drought was sufficient to actually interrupt growth for our trees. And we need more data to really understand the full impacts in terms of the magnitude of growth and to have a comparison year. And so this is hopefully why you can see the value in this kind of monitoring to really understand. So when we're making decisions about what trees to plant or what species to thin out, that we're choosing species that are more resilient or perhaps less adapted for that area, and we want to remove that tree from our woodlot, for example, over another species. And so ongoing work, we're keeping this network going. It's a long-term initiative, and we're hoping to really understand the full impacts of this drought with this year of data in terms of potential legacy effects. So my colleague has seen before that it's the year after a drought or a frost event or even a hurricane sometimes, that then we'll see a signature in the radial growth patterns. So I'm looking forward to capturing the data for this year to really understand. And we're also waiting on a detailed characterization of our sites with some soil samples that we've collected. So that'll help us to understand that maybe some sites were less impacted based off of their soil texture or quality. And we're also collaborating with some researchers across Canada and the US as well as Switzerland to pool our observations and develop new models of radial growth to be able to predict and model radial growth under future conditions. And we just launched our website 2 weeks ago, so it's very much in the early stages, but if you want to log in or just see our website, you can see. Eventually, we're going to have a kind of a status update every time we collect data. We'll plug it into the website so you can see for this species or this location how many days were the trees able to grow across the province. And so you can also visit me at my stand out there. I have some pamphlets and some business cards so you don't have to write that website down. And we'd love to hear from you if there's something that you're particularly interested in, you want to see more coverage of a certain species or perhaps a different variable. We're really open to expanding and trying out different things. And we just published a paper on our network in the 100th anniversary edition of the Forestry Chronicle. If any of you are interested in the Forestry Chronicle, just describing our network and our goals and kind of the theoretical basis for our infrastructure. And yeah, thank you all so much.